Hey there, friend. Welcome to a place where time slows down for you and you can relax. Tonight, let's explore something truly strange and beautiful, a form of matter that moves forever, even when nothing seems to be pushing it. We will explore the phenomenon of the time crystals. So get cozy, let your thoughts drift, and let's gently wander through the rhythm of time itself. Chapter 1. What is a time crystal? Imagine holding a perfectly cut diamond, its internal structure repeating so precisely that its atoms form an unchanging lattice in space. Each unit cell, each repeating section of its geometry aligns with the next like a molecular-level mirror, extending in 3 dimensions. This regularity, this symmetry in space, is the defining feature of what we call a crystal. Whether it's a diamond, a snowflake, or salt, these materials are formed by atoms locked into patterns that extend in space over and over with a kind of elegant mathematical rhythm. Now, what if something like that could happen not just in space, but in time? This is the idea behind a time crystal, a phase of matter that exhibits regular, repeating behavior, not just in where its atoms are, but in when they are. Like a crystal that repeats across distance, a time crystal repeats across time. It pulses, it cycles, it moves forever through time in a stable and predictable rhythm. And it does so without any input of energy. It's not a clock, powered by a battery or wound by a spring. It's not a pendulum swinging because of gravity. It's something fundamentally different, a system that oscillates indefinitely without using energy. In a world governed by entropy and decay, this idea sounds impossible, and for a long time it was believed to be. The concept of a time crystal was first proposed by Nobel Prize-winning physicist Frank Wilczek in 2012. He was exploring the deep connections between symmetries and physical laws. In physics, a symmetry means that certain properties of a system remain unchanged under some transformation. For example, a crystal in space breaks what's called spatial translation symmetry. The laws of physics are the same everywhere, but the crystal itself isn't. It has regions that look different from one another because its structure repeats. Wilczek asked, could a system break time translation symmetry in a similar way? That is, could it look different at different moments in time, even when the underlying laws of physics are perfectly uniform? It's a subtle question. Most physical systems that repeat in time do so only with an external push, an input of energy like a pendulum clock that eventually winds down if left alone. But Wilczek imagined something that could spontaneously oscillate in its lowest energy state. This lowest energy state, known as the ground state, is typically motionless. For instance, in a block of ice cooled to absolute zero, the atoms are arranged in a perfectly still crystal. There is no residual motion, no rhythm, no pulse. Yet Wilczek's proposed time crystal would continue to cycle even in its ground state. That's what made the idea so radical. It seemed to challenge one of the bedrock principles of physics, that energy must be conserved and systems naturally fall into stillness if there's no external drive. Initial reactions from the scientific community were skeptical, and for good reason. Some physicists argued that such perpetual motion would violate the laws of thermodynamics. Others pointed out that in equilibrium physics, the kind that governs traditional crystals and materials, a time crystal simply couldn't exist. Systems in equilibrium, by definition, don't exhibit spontaneous periodic motion. But as often happens in science, skepticism led to exploration. Physicists began asking, is there a different context, perhaps outside of equilibrium, where something like a time crystal might emerge? This shift in perspective turned out to be the key. Instead of looking for time crystals in systems at rest, researchers began to look in systems that were being periodically driven. These are systems that are not in equilibrium, but are kicked or pulsed at regular intervals, like a strobe light flashing on and off, or a laser nudging atoms in a regular rhythm. These are called Floquet systems, named after the French mathematician Gaston Floquet, who studied periodic differential equations. In a Floquet system, even though energy is being put in from the outside, the system can sometimes settle into a special kind of stability, a behavior that's locked into a cycle that repeats at a different rhythm than the drive itself. This is where the time crystal comes to life. In 2016, physicists at Princeton, Harvard, and UC Berkeley began exploring this idea more rigorously. They proposed a model where a collection of interacting quantum spins, a sort of simplified magnetic system, was driven periodically in time. Crucially, the system included disorder and interactions that prevented it from heating up, a phenomenon known as many-body localization. This prevented the energy from the periodic drive from scrambling the system, allowing it to settle into a robust repeating pattern. The result was astonishing. In these models, the spins began to flip back and forth at twice the period of the drive. That is, if the system was being kicked once every second, the spins responded once every 2 seconds. This subharmonic response, this breaking of the drive's time translation symmetry, was the hallmark of a discrete time crystal. The system found a new rhythm, not dictated by the external pulse, but by its own internal order. It was as if a dancer, being tapped on the shoulder once every beat, chose to move only every other beat and kept doing so without fail, indefinitely. In 2021, researchers at Google, using their quantum computing hardware, demonstrated the first clear experimental realization of a time crystal. They used a chain of superconducting qubits, quantum bits that can represent 0, 1, or a superposition of both, and drove them periodically using precise microwave pulses. What they observed was a repeating pattern of quantum states that persisted far longer than expected, resisting decoherence and disorder. These oscillations weren't random or decaying. They followed a steady beat, distinct from the rhythm of the pulses themselves. This was the behavior predicted by theory. The time crystal had stepped from the realm of thought experiments into reality. But what makes time crystals so fascinating is not just that they exist, it's what they imply. In ordinary matter, the lowest energy state is static. A rock at the bottom of a hill doesn't move unless something pushes it. But in a time crystal, the lowest energy state isn't static, it moves. And yet it doesn't radiate energy, doesn't warm up, doesn't run down. It's a kind of motion without motion. This isn't perpetual motion in the classical sense. It doesn't do work or violate thermodynamics. But it's still deeply non-intuitive, and it opens new windows into the behavior of quantum systems far from equilibrium. So what exactly is a time crystal? It's a phase of matter in which particles arrange themselves in a pattern that repeats in time, not just in space. This temporal order is stable and self-sustaining. It emerges not from energy inputs, but from the peculiarities of quantum entanglement, disorder, and periodic driving. It exists only in the quantum world, where particles can exist in superpositions, interfere with themselves, and respond to collective patterns rather than individual pushes. It is a structure in time, one that defies stillness and persists in motion, even in the absence of force. Unlike a grandfather clock that eventually slows, or a music box that winds down, a time crystal does not decay in the same way. It can, in principle, oscillate forever, an unending rhythm built into the very laws of quantum mechanics. It's not just a new material, it's a new kind of temporal order, a new way for the universe to organize motion. And because it exists only in non-equilibrium systems, it invites us to reconsider what stability really means. Is equilibrium the only form of balance? Or can some systems find harmony in motion itself? As we begin to understand time crystals more deeply, we may also begin to understand the strange borderlands where time, energy, and information meet. This isn't just a novelty, it's a doorway to a deeper understanding of quantum behavior, and possibly a stepping stone to quantum technologies that harness time in new ways. And perhaps, most hauntingly, the time crystal reminds us of a deeper truth, that not all stillness is motionless, and not all change requires a cause. In a universe ruled by entropy, a system that dances forever may be the closest thing we have to permanence. Chapter 2: The Strange Birth of an Idea, Frank Wilczek's Thought Experiment. In the history of physics, some of the most profound discoveries have begun not with experiments or observations, but with pure thought. The thought experiment has long been a trusted companion of theoretical physicists, a way to push against the boundaries of the known, to question the axioms of the present, and to wonder whether the universe might permit something stranger, deeper, or more elegant than our current models allow. In 2012, Frank Wilczek, a Nobel Prize-winning physicist known for his work on quantum chromodynamics, ventured into one of these conceptual borderlands. He posed a question that at first seemed absurd. If spatial crystals are defined by a repeating pattern in space, could there be objects defined by a repeating pattern in time? Could there be a form of matter that naturally cycles or pulses, not because it is driven or powered, but because its lowest energy state is inherently dynamic? This question wasn't asked casually. It arose from the deep mathematical relationships between symmetry and conservation laws, principles that sit at the foundation of modern physics. In particular, Wilczek was working within the framework of quantum field theory and classical mechanics, reflecting on the implications of what happens when certain symmetries are spontaneously broken. In physics, symmetry isn't about aesthetics. It's a powerful language for describing the invariance of systems. If a system looks the same after being shifted in space, it possesses spatial translation symmetry. If it looks the same at any point in time, it has time translation symmetry. In many of the physical systems we know, these symmetries are baked into the laws themselves, even if the outcomes break them. A classic example of this is the spatial crystal. The laws of physics themselves do not favor any one location in space over another. But when atoms cool and form a solid crystal, they arrange themselves in a structure that is not the same everywhere. This symmetry breaking gives rise to the familiar lattice structure of crystals. The regularity is not in the laws, but in the outcome of the system settling into its lowest energy configuration. The pattern emerges because that's what the system prefers, even though the laws themselves are spatially uniform. Wilczek's idea was to extend this concept into the temporal domain. If the laws of physics are symmetric in time, meaning they don't prefer one moment over another, could a system nevertheless choose a state that breaks that symmetry? Could it spontaneously settle into a mode where it cycles through a pattern at regular intervals over and over again in time? This wouldn't just be a system responding to an external drive, like a metronome powered by a battery. It would be a new kind of ground state, one that never sits still. He called this hypothetical structure a time crystal. At first glance, this proposal raised significant eyebrows. Time, unlike space, is tightly constrained by the second law of thermodynamics. In classical systems, motion without energy input leads inevitably to decay. Friction, heat dissipation, and entropy ensure that systems trend toward equilibrium. Oscillations die out, patterns smooth over. But Wilczek was proposing that, in the strange world of quantum mechanics, something fundamentally different might be possible. A lowest energy state that is not static but perpetually in motion. To illustrate this idea, Wilczek developed a simple theoretical model. A ring of charged particles interacting with one another and responding to electromagnetic fields. Under certain configurations, he argued, the particles could organize themselves into a structure that not only broke spatial symmetry, forming a repeating pattern around the ring, but also broke time symmetry by rotating periodically, even in the absence of external force. The motion would be spontaneous and self-sustained. He showed mathematically that the system's ground state might not be time invariant, even if the underlying equations were. If true, this would have been a new kind of quantum order, one that violated what had previously been considered a necessary condition for equilibrium. But this interpretation quickly met with resistance from the physics community. Critics pointed out a fundamental issue. In quantum mechanics, the ground state of a system is by definition a stationary state. It doesn't evolve in time except for a trivial phase factor. Any true time-dependent oscillation, they argued, must involve excitations above the ground state, which means energy would have to be added to the system. That contradicts the requirement for a ground state to be the lowest energy configuration. In this sense, what Wilczek had proposed appeared to be a kind of perpetual motion machine, not in the mechanical sense, but in the deeper thermodynamic sense. Motion without energy consumption, in equilibrium, forever. Multiple papers were published in rapid succession, arguing that such a system could not exist. It was pointed out that if time translation symmetry is broken, the system cannot be in its ground state in the conventional sense. This led many to conclude that Wilczek's proposed time crystal was mathematically elegant but physically impossible. In equilibrium, time symmetry breaking appeared to be ruled out. But as the dust settled, something remarkable happened. Instead of abandoning the idea entirely, physicists began to reinterpret and recontextualize it. What if time crystals weren't equilibrium systems at all? What if they emerged only in driven, non-equilibrium settings, systems periodically nudged or pulsed, but where the response is fundamentally new? These are known as flochet systems, and, unlike equilibrium systems, they allow for behavior that doesn't fit into the standard thermodynamic framework. In 2016, theoretical work by physicists at Harvard and Princeton reframed the concept in this way. They proposed that under certain conditions, specifically in periodically driven quantum systems with disorder and interactions, it might be possible to observe a phase of matter that breaks discrete time translation symmetry. The system would be driven at one frequency but respond at a different one, settling into a stable subharmonic mode that repeats over time. Crucially, this behavior could persist indefinitely, even in the presence of small perturbations, due to the phenomenon of many-body localization. Wilczek's original idea had transformed. It no longer required a ground state that oscillates perpetually in equilibrium. Instead, it became a new kind of phase in driven quantum systems, robust and stable, but far from equilibrium. This revised version of a time crystal gained traction because it respected the known laws of thermodynamics while still exhibiting the core idea, a spontaneously ordered structure in time. The intellectual evolution of time crystals reflects an important truth about science. Revolutionary ideas are often met with resistance, not because they are wrong, but because they challenge the deeply held frameworks through which scientists interpret the world. Wilczek's initial proposal wasn't wrong. It simply pointed toward a phenomenon that required a new conceptual lens. He lit the spark, and others refined the fire. His theoretical time crystal planted a seed that would later grow into a verified experimental discovery. In 2021, this reinterpretation culminated in real-world demonstrations of time crystal behavior using quantum computing platforms. Experiments at Google and other institutions confirmed that when qubits were arranged, coupled, and driven in the right way, they could enter a state of stable, repeating oscillations, a time crystal in the discrete, driven sense. The physics community had gone from rejection to realization in less than a decade, all because a theoretical physicist dared to ask a question that didn't quite fit into the accepted mold. Wilczek's journey with the time crystal also reveals a subtler, more philosophical undercurrent in theoretical physics. At its best, physics doesn't just describe what is, it dares to ask what could be. It's not content with cataloging nature's patterns. It seeks to understand why those patterns arise and whether others might be hiding just out of reach. The idea of a time crystal wasn't pulled from experimental data. It emerged from mathematical symmetry and a willingness to take those symmetries seriously, even to their most unusual conclusions. In hindsight, it's clear that Wilczek's proposal didn't predict a new material in the traditional sense. Rather, it cracked open a conceptual door into a new class of quantum phases, ones that only emerge under specific conditions far from equilibrium, where the familiar rules bend and new kinds of order can appear. This is the terrain of modern condensed matter physics, where structure, symmetry, and stability are reimagined in light of quantum entanglement and complexity. The story of time crystals is still being written, but it began with a question posed not in a laboratory, but in the quiet logic of the mind. Could matter pulse in time the way it arranges in space? The answer, as it turns out, is yes, but only if we're willing to look beyond equilibrium, beyond static definitions of order, and into the shimmering dynamics of the quantum world. And somewhere in that quiet dance of theoretical symmetries and shifting assumptions, we find a glimpse of something more. Not everything that endures must stand still. Some things persist by moving, and in their rhythm, they whisper that time, too, may have hidden structures we have only just begun to see. Chapter 3. Breaking Symmetries, the hidden rule of all physics. Symmetry, at its core, is a principle of sameness. It is the idea that certain properties of a system remain unchanged under a transformation, whether it's rotating a shape, shifting a position, or advancing time. In physics, symmetry is not simply a matter of beauty or visual appeal. It is a profound organizing principle that guides the laws of nature at every level, from the smallest particles to the structure of space-time itself. When something in the physical world breaks a symmetry, it reveals information. It creates structure. It becomes distinguishable. And often, this broken symmetry underlies the emergence of the physical phenomena we observe every day. In classical mechanics, symmetry is relatively straightforward. A spinning wheel, for example, has rotational symmetry. It looks the same no matter how you turn it. A calm lake has reflection symmetry, its surface mirroring the world above it. But in physics, symmetry has a far deeper meaning. It connects the uniformity of nature with the conservation of quantities. According to Noether's theorem, formulated by mathematician Emmy Noether in the early 20th century, every continuous symmetry in nature corresponds to a conserved quantity. If the laws of physics are the same across space, momentum is conserved. If they are the same in time, energy is conserved. This connection is not merely conceptual, it is the engine of modern theoretical physics. But symmetry is not just about what remains unchanged. It is just as much about what changes, what gets broken. When a symmetry is broken, it reveals an asymmetry that wasn't previously there. This breaking is not an error or flaw. Rather, it is a natural process by which the universe develops structure. A system governed by symmetrical laws can settle into a configuration that is not symmetrical. It is through the breaking of symmetry that complexity, pattern, and form arise. This is why symmetry breaking is so important in understanding physical systems. It tells us not only what is possible, but what actually emerges. One of the simplest and most illustrative examples of symmetry breaking occurs during the cooling of a material. Imagine a liquid composed of atoms floating freely, arranged randomly and uniformly. At high temperature, the atoms are constantly jostling around, their energy too high for them to settle into any ordered state. The liquid, at this point, has continuous spatial symmetry. It looks the same no matter where you look. But as the liquid cools, the atoms begin to lose energy. They start to settle into positions of lower potential energy, aligning themselves with their neighbors. Eventually, the system undergoes a phase transition. It becomes a crystal. A crystal is not spatially uniform. It breaks the continuous spatial symmetry of the liquid by choosing specific positions in space to place its atoms. It is as if, from a smooth and indistinct background, a precise grid appears, carving regularity into randomness. This new order is stable, not because the laws of physics changed, but because the system itself chose, among many equally possible configurations, one that reduced its energy in the most efficient way. The underlying laws remained symmetric, but the outcome did not. This same principle holds across physics. In magnetism, a collection of atoms with magnetic moments may, at high temperatures, point in random directions, disordered, symmetric. But as the system cools, they may begin to align, pointing in the same direction. The rotational symmetry of the system is broken. There is now a preferred direction, an axis of magnetization, where none existed before. This spontaneous breaking of symmetry gives rise to magnetic order. In the early universe, symmetry breaking played an essential role in shaping the cosmos. According to the standard model of particle physics, the forces we know today, gravity, electromagnetism, the weak and strong nuclear forces, were once unified under a single force in the earliest moments after the Big Bang. As the universe cooled and expanded, this unified symmetry began to break. The different forces emerged through a series of symmetry-breaking phase transitions, each one leaving behind a universe that was increasingly structured, increasingly differentiated. Without symmetry breaking, there would be no separation of forces, no particles with different masses, no chemistry, no stars, no life. This framing makes it clear that symmetry and the breaking of symmetry is not just a formal concept. It is an engine for the universe's evolution. It is the means by which abstract, uniform potential becomes concrete, diverse reality. But not all symmetry breaking is obvious. In quantum mechanics, the landscape of symmetry is stranger and more subtle. Quantum systems are described by wave functions, which encode the probabilities of outcomes rather than certainties. These wave functions can exhibit symmetries that are not visible until they are broken, either spontaneously by the system's dynamics or through interaction with an external observer. In certain quantum systems, especially those involving many interacting particles, the ground state may break a symmetry even if the Hamiltonian, the fundamental energy equation of the system, does not. This is spontaneous symmetry breaking at the quantum level. This is precisely the kind of reasoning that led to the idea of time crystals. If a system can break spatial symmetry to form a crystal, could it also break time symmetry? That is, could it exhibit a preferred rhythm or periodicity, even though the governing laws are time invariant? Time crystals, in their final form as discrete time crystals, emerge not from the breaking of continuous time symmetry, but from the breaking of discrete time translation symmetry. In other words, a system that is periodically driven at one frequency might respond at a different frequency, settling into a rhythm that defies the timing of the drive itself. This is a type of temporal symmetry breaking, a system choosing a different beat from the one being played. To appreciate the depth of this idea, it's important to understand how symmetry breaking differs between space and time. In spatial symmetry breaking, the system settles into a configuration that does not look the same everywhere, even if the laws say it could. In temporal symmetry breaking, the system evolves in a way that does not repeat with the same regularity as its governing dynamics. And yet, this evolution is not chaotic. It is ordered, stable, and predictable. In discrete time crystals, the symmetry being broken is not that of ordinary continuous time, but of a periodic external force. The drive acts as a kind of ticking metronome, nudging the system at regular intervals. Most systems respond to this drive with motion that matches its rhythm. But a time crystal responds differently. It chooses to oscillate at a multiple of the drive period, say once every 2 ticks instead of every 1. This subharmonic response breaks the symmetry of the input and reveals a deeper structure, a rhythm chosen by the system, not imposed on it. What makes this symmetry breaking particularly fascinating is that it is robust. In ordinary physical systems, small disturbances can disrupt periodic behavior, but time crystals, once formed, can resist such disturbances. This robustness is a hallmark of symmetry-protected phases. Phases of matter where the pattern persists even when the details are slightly altered. This is why time crystals are not just clever tricks of timing, but genuine phases of matter in the quantum sense. Understanding the role of symmetry breaking in time crystals also helps distinguish them from simple driven oscillators. A pendulum, for instance, responds to gravity and air resistance with a natural frequency, but it eventually loses energy and slows. A time crystal, by contrast, exists in a state of perpetual oscillation that is not powered in the conventional sense. Its motion is a consequence of symmetry breaking, not continuous energy flow. It is an emergent order in time, protected by the underlying quantum properties of the system and its resistance to thermalization. All of this ties back to a broader realization in physics. Symmetries and their breaking are not just tools for solving equations. They are the language by which the universe expresses its possibilities. Symmetry tells us what could be. Broken symmetry tells us what is. And as we probe deeper into the quantum world, we find that even time, the most fundamental backdrop of all physical experience, can host its own forms of order, its own fractures, its own patterns waiting to be revealed. In the grand arc of physical theory, symmetry breaking is the quiet mechanism behind so much of what we take for granted. It is why there are structures in the universe at all. It is why particles have mass, why materials have phases, why the early universe gave rise to stars and galaxies instead of remaining a featureless fog. And now, with the discovery of time crystals, we glimpse a new chapter, one in which time itself can be carved into rhythm, into repetition, into structure, born from the breaking of something deeper than we ever imagined. It invites a final, quiet reflection. If symmetry is the canvas on which the laws of physics are painted, then broken symmetry is the brushstroke that brings the universe to life. Perhaps even in our own lives, it is the imperfection, the departure from sameness, that makes things meaningful. The cosmos is not silent. It hums with broken symmetries, and in their echoes, we find the pulse of reality. Chapter 4. The quantum nature of time crystals. To truly understand time crystals, one must step beyond classical physics and enter the peculiar realm of quantum mechanics. While earlier chapters discussed time crystals as a new phase of matter that breaks time translation symmetry and explored how their behavior depends on driven non-equilibrium systems, we have yet to fully unpack what it means for a system to behave this way at a quantum level. The nature of time crystals is inherently quantum. They do not emerge in classical physics, and their stability, coherence, and repeating behavior depend on phenomena that have no classical counterpart. In a universe governed only by Newtonian laws, time crystals could not exist. Their existence is one of the clearest illustrations of how deeply strange and deeply structured the quantum world really is. At the heart of quantum physics lies the principle of superposition. Unlike classical objects, which exist in well-defined states, quantum systems can exist in combinations of states simultaneously. A single particle can be both here and there, spin up and spin down until measured. These possibilities are encoded in a mathematical object called the wave function, which evolves deterministically through the Schrödinger equation, but collapses upon observation into a definite outcome. The quantum world is probabilistic, entangled, and governed by principles that defy our everyday experience. This is the canvas on which time crystals form. The kind of time crystal that has been realized experimentally is called a discrete time crystal. It does not break continuous time translation symmetry, but instead breaks a discrete one. The system is driven periodically, given a kick or pulse at regular intervals. But instead of responding in time with the rhythm of the drive, the system spontaneously chooses a longer period. It oscillates with a subharmonic response. This behavior is quantum in nature for two fundamental reasons. First, it requires coherence across a many-body system. Second, it relies on mechanisms that prevent heating, processes unique to quantum dynamics. In a driven system, one expects energy to accumulate. Periodically adding energy to a quantum system typically causes it to heat up until it reaches thermal equilibrium, where all order is lost, and the system becomes a featureless collection of excitations. This is problematic because the repeating behavior that defines a time crystal would be destroyed by such heating. To prevent this, time crystals must exploit a remarkable quantum phenomenon, many-body localization. Many-body localization is a property of disordered quantum systems that allows them to avoid thermalization, even when they are driven. In most systems, energy and information spread through interactions, causing the system to equilibrate. But in a many-body localized system, disorder, randomness in local energies or coupling strengths, causes quantum interference that prevents this spreading. The particles become trapped, unable to share their energy freely. This localized behavior allows the system to maintain memory of its initial state and avoid heating even under a periodic drive. The result is a stable, non-equilibrium phase, a setting in which a time crystal can emerge. In a time crystal, the system responds not by decaying or randomizing, but by developing a kind of temporal long-range order. Quantum spins, for example, might flip back and forth in perfect synchronization with one another, but at twice the period of the drive. This synchronization persists because of entanglement. In quantum mechanics, entanglement is the linking of states such that the measurement of one instantaneously affects the outcome of another, no matter the distance between them. In time crystals, entanglement plays a stabilizing role. It allows the oscillations of one part of the system to reinforce the oscillations of the rest, binding the entire structure into a collective dance that is immune to small disturbances. This is a key distinction from classical systems. In a classical-driven oscillator, there is no concept of entanglement. Each part behaves independently. There is no way for one region to enforce coherence in another without direct interaction. But in quantum systems, entanglement allows correlations to propagate without direct communication, creating a kind of internal feedback loop that maintains the system's structure. This collective quantum behavior is what allows time crystals to exhibit their extraordinary temporal ordering. The experimental realization of time crystals uses systems of qubits, quantum bits, that can be individually controlled and measured. In superconducting qubit arrays, like those used by Google, or trapped ion systems, researchers prepare a line of qubits and apply a sequence of operations designed to drive the system periodically. Each operation typically involves flipping spins, applying disorder through randomly varied magnetic fields, and coupling qubits in a controlled fashion. The system is initialized in a known quantum state and then evolves through many cycles of this drive. In the presence of many-body localization, and with a properly tuned drive, the qubits begin to oscillate. Crucially, these oscillations do not match the timing of the drive. They occur with a different frequency, often exactly twice the drive period, a hallmark of period doubling symmetry breaking. This subharmonic response is not programmed into the system. It arises spontaneously. The qubits fall into a rhythm, and this rhythm is stable over time. Even when small imperfections are introduced, noise in the drive, slight deviations in the coupling, the system maintains its behavior. This robustness is a key feature of a true time crystal. It distinguishes genuine spontaneous symmetry breaking from mere engineered resonance. This kind of temporal order is a new category in the landscape of quantum phases. Unlike spatial crystals, which exhibit long-range order in space, time crystals exhibit long-range order in time. This means that the correlations between the state of the system at one moment and another do not decay, even over many cycles. In statistical mechanics, most systems lose memory of their past. But a time crystal remembers. It remembers because it is protected, not by an absence of change, but by a structured pattern of change, repeating over and over in time. This raises deep questions about the nature of time in quantum mechanics. Traditionally, time is treated as a parameter, not an observable. Quantum systems evolve with respect to time, but time itself is not subject to quantum uncertainty or superposition. Yet in time crystals, time takes on a new character. It becomes something that can be ordered, broken, and structured, much like space. The distinction between time as a background and time as a dynamic feature begins to blur. And while time crystals do not allow for time travel or reversal, they suggest that time may be more malleable than previously thought, capable of supporting its own forms of coherence and pattern. Furthermore, time crystals challenge our notions of equilibrium and stability. In classical thermodynamics, stability is associated with rest, a system at equilibrium, energy uniformly distributed, motion ceased. But time crystals show that in the quantum world, there is another kind of stability, dynamic stability. A system can be in motion perpetually, not because it is being pushed, but because motion is the most ordered, lowest energy behavior it can assume within the constraints of its quantum architecture. This redefinition of stability opens new avenues in the study of quantum matter, suggesting that many other non-equilibrium phases may yet be discovered. It is worth noting that time crystals are still in their infancy. The systems that demonstrate them are small, typically involving a few dozen qubits, and they require highly controlled environments. But as quantum computing platforms grow in complexity and coherence, time crystals may become easier to study, manipulate, and perhaps even apply. There are already theoretical proposals for using time crystals in quantum information processing, where their stable oscillations could serve as a new kind of memory or logic gate. Their robustness against noise and disorder could make them useful in error-resistant quantum architectures. As the field matures, researchers are exploring whether time crystals can exist in higher dimensions, with more complex symmetries, or in open systems coupled to environments. These extensions may reveal further layers of quantum behavior, some of which could challenge our current understanding even more deeply. The time crystal, far from being a curiosity, may be the first glimpse of an entire class of exotic quantum phases that exist only in driven, out-of-equilibrium conditions. All of this underscores a profound shift in physics. For centuries, the goal was to understand systems at rest, in equilibrium, where energy is minimized and entropy plays its slow, inevitable role. But now we are beginning to see that some of the most fascinating phenomena occur far from equilibrium, in systems that are driven, disordered, and delicately balanced. Time crystals live in this realm. They are not exceptions to the laws of physics, but revelations of a deeper order that only becomes visible when systems are pushed out of stillness and allowed to find their own surprising rhythms. In the stillness of classical physics, motion must be caused. In the quantum world, motion can be a natural state, spontaneous, ordered, and eternal. And perhaps, in the subtle heartbeat of a time crystal, we catch a glimpse of something that defies our deepest intuitions. That even in the quietest corners of the universe, time itself may learn to dance. Chapter 5: How Scientists Created a Time Crystal in a Lab. In the abstract world of theoretical physics, time crystals were long considered a speculative concept, an elegant mathematical possibility whose realization remained uncertain. But theory alone is never the endpoint in science. Ideas, no matter how elegant, must be tested against nature. For years after Frank Wilczek's initial thought experiment, time crystals existed only in the minds of physicists and in the pages of peer-reviewed journals. Yet in 2021, a remarkable transformation took place. What began as a theoretical curiosity became a concrete reality, as scientists created time crystals in controlled laboratory conditions. These were not theoretical models or simulations, but physical systems exhibiting the core behavior predicted by the theory. A spontaneously emerging, stable oscillation in time that broke the symmetry of the periodic drive. This achievement marked a significant step not just in understanding time crystals, but in expanding the frontier of quantum engineering itself. To bring a time crystal into existence, researchers needed to navigate the constraints of quantum systems far from equilibrium. The key challenge was avoiding thermalization. In most driven quantum systems, repeated application of energy causes the system to heat up and eventually lose any ordered behavior. This would destroy the regularity required for a time crystal to form. The solution to this problem lay in a phenomenon known as many-body localization, where disorder and quantum interference combine to prevent the spread of energy and preserve coherence over long periods of time. Building on this understanding, physicists began designing systems that incorporated these protective features. One of the earliest experimental breakthroughs came from a collaboration between theorists and experimentalists working with trapped ions. These ions, atoms stripped of one or more electrons, can be held in electromagnetic fields and manipulated with extraordinary precision. Using laser pulses, researchers can entangle ions, flip their spins, and drive them in periodic ways that mimic the theoretical models of discrete time crystals. In one such experiment, a chain of ytterbium ions was used. Each ion's spin acted as a qubit, and the spins were periodically flipped and allowed to interact with each other through long-range couplings. The system was initialized, driven repeatedly, and monitored. What they observed was the emergence of a robust oscillation at twice the period of the drive, a hallmark of subharmonic response. This behavior was not due to external synchronization or fine-tuned control. In fact, the remarkable feature of this result was that it persisted even when the drive was slightly altered. The system naturally fell into a repeating rhythm that defied the timing of the pulse sequence. The oscillation did not decay rapidly, nor was it sensitive to small imperfections. It was stable, repeatable, and consistent with the behavior predicted for a discrete time crystal. This experiment demonstrated that time translation symmetry could be broken in a periodically driven quantum system under the right conditions. But perhaps the most celebrated realization came from researchers at Google, who employed a radically different platform, a programmable quantum processor made of superconducting qubits. This system, known as Sycamore, had already gained attention in the quantum computing world for achieving what was described as quantum supremacy, the ability to perform a task beyond the practical reach of classical computers. Now, the same technology was used to create a new phase of matter. In this experiment, 20 qubits were arranged in a line and subjected to a carefully engineered sequence of quantum gates that alternated between disorder, spin flips, and entangling operations. The qubits were periodically driven, with each cycle designed to resemble the theoretical model for a time crystal. The researchers began by initializing the qubits into a known quantum state. They then applied the driving sequence for up to hundreds of cycles, measuring the state of each qubit after every iteration. What emerged was clear. The system fell into a repeating pattern that oscillated at twice the period of the drive, and this behavior persisted for a remarkably long time relative to the coherence properties of the qubits. The signature of a time crystal, a spontaneously chosen subharmonic oscillation, was unmistakable. Moreover, the oscillation was not imposed externally, It arose spontaneously from the internal dynamics of the system. What made this result even more striking was its robustness. Time crystals are not fragile resonances. They are stable phases of matter, protected by symmetry and many body interactions. In the Google experiment, even when the researchers introduced noise or adjusted the parameters slightly, the oscillations remained. This kind of resilience is a hallmark of phase stability, akin to how a magnet retains its polarization under small perturbations. The time crystal, once formed, locked into a pattern that could not be easily disturbed. It was, in the quantum sense, an emergent order in time. Importantly, the researchers were able to verify that the system did not thermalize during the experiment. Despite being driven repeatedly, the qubits did not absorb energy in the way most systems would. This confirmed that the conditions necessary for a time crystal, namely periodic driving, disorder, and localization, had been met. The experiment offered strong evidence that time crystals are not just theoretical possibilities, but real phases of matter that can be engineered, studied, and perhaps one day harnessed. The creation of time crystals in a lab required more than just theoretical insight. It demanded technological precision in areas such as qubit control, coherence maintenance, and quantum gate fidelity. These are non-trivial challenges. Quantum systems are notoriously delicate. They are susceptible to noise from the environment, fluctuations in temperature, and decoherence from imperfect isolation. Yet by overcoming these barriers, scientists demonstrated not only that time crystals can exist, but that they can be realized with present-day quantum hardware. The significance of these experiments goes beyond the novelty of making a new phase of matter. Time crystals represent a new kind of order, one that arises not in the quiet stillness of equilibrium, but in the active context of periodic driving and sustained interaction. They are examples of non-equilibrium phases, which may be just the beginning of a broader classification of exotic states in quantum systems. As researchers continue to explore these regimes, more such phases may be discovered, each revealing new dimensions of the quantum landscape. Moreover, the techniques used to create time crystals are pushing the boundaries of what quantum computers can do. These systems are not just platforms for computation, they are becoming tools for exploring fundamental physics. The line between computing and condensed matter experimentation is beginning to blur. Quantum processors like Sycamore are capable of simulating complex dynamics, testing theoretical predictions, and enabling experiments that would be difficult or impossible in traditional materials. This marks a new era of quantum simulation, where the laboratory itself is programmable and the boundaries of theory and practice begin to dissolve. There are open questions that remain. Time crystals have been demonstrated in one-dimensional systems. Can they be extended to 2 or even 3 dimensions? Can they exhibit more complex forms of symmetry breaking, such as quasi-crystalline or topological time structures? Can they be realized in systems that are open to the environment, or are they fundamentally limited to closed, isolated setups? And perhaps most intriguingly, can they be used for something? Can the stable oscillations of a time crystal serve as a clock, a memory, or a quantum device? Some proposals already suggest practical applications. Because time crystals exhibit a stable, repeating pattern, they might serve as components in quantum memory, where coherence over long periods is essential. Their resistance to decoherence and noise could make them candidates for use in quantum error correction, one of the greatest challenges in building scalable quantum computers. And while these applications remain speculative, the foundational understanding gained from these early experiments is likely to inform the development of future quantum technologies. But even without immediate application, the creation of a time crystal in a lab is a remarkable achievement in its own right. It demonstrates that quantum systems can exhibit order not just in space, but in time. It shows that the principles of symmetry breaking extend beyond the familiar and into the temporal domain. And it reveals that the quantum world, far from being a realm of chaos and uncertainty, can support deeply ordered patterns that emerge and persist without external cause. There is something quietly profound about this. A time crystal does not move because it is pushed. It moves because motion is its most natural state. It dances to a rhythm it creates for itself. In the stillness of the vacuum, amid the silence of isolation, it pulses, not because it must, but because it can. And perhaps that is the most poetic aspect of the discovery. In a universe ruled by entropy, where systems decay and motion ceases, the time crystal offers a rare defiance. It is motion without energy, order without force, memory without decay. In its heartbeat, there is a kind of permanence, a whisper that not all things are destined to stop. Chapter 6. Motion without energy. How time crystals defy intuition. To those grounded in classical physics, the concept of motion without energy is not just counterintuitive, it seems categorically impossible. In our everyday experience, every form of motion must be powered. A pendulum eventually stops swinging unless it is re-energized. A car will roll to a halt without fuel. Even celestial bodies, though seemingly eternal in their revolutions, are subject to gravitational radiation and drag in the very long term. The idea that a system could move perpetually without the expenditure or input of energy appears to violate some of the most deeply ingrained principles of physics. Time crystals, however, compel us to rethink what motion, energy, and stability truly mean, particularly within the quantum domain. In a classical setting, motion is always tied to energy exchange, but time crystals operate in a realm governed by quantum mechanics and many-body physics, where energy conservation, symmetry, and state evolution follow different rules. Their motion is not mechanical, it is not classical. It is, in a profound sense, structural. It is not motion through space, but a rhythm within the quantum state itself, a pattern that unfolds in time indefinitely, even when the system resides in its lowest energy configuration or steady state. To understand why this is possible, we must revisit what motion means in this context. A time crystal is not spinning like a wheel or vibrating like a string. Instead, its quantum degrees of freedom, such as the spin orientations of particles, change periodically over time. In a discrete time crystal, for example, the spin state of a system flips or oscillates with a period longer than that of the external drive. If the system is being pulsed once per second, it might flip every 2 seconds. This is not imposed from outside. It is an emergent behavior arising spontaneously from the internal interactions of the system. What makes this truly strange is that the system is not absorbing energy from its environment. In fact, absorbing energy would destabilize the time crystal, causing it to heat up and lose coherence. Time crystals thrive in systems that resist heating thanks to mechanisms like many-body localization or pre-thermalization. These mechanisms prevent the system from equilibrating in the usual thermodynamic sense. In a time crystal, the drive does not deliver usable energy in the form of work or heat. Instead, it serves as a regular metronome, providing structure but not motion in the energetic sense. From a thermodynamic perspective, this seems puzzling. The second law of thermodynamics tells us that systems evolve toward states of greater entropy. Left alone, any organized structure should eventually disintegrate into disorder. Yet time crystals maintain order in the time domain. They cycle through distinct states over and over, resisting decay. This is possible only because they are fundamentally non-equilibrium systems. They are not governed by the usual laws that apply to systems at rest or in thermal equilibrium. Instead, they belong to a class of driven, periodically forced quantum systems, where the rules shift subtly but significantly. In such systems, the idea of a ground state, usually associated with a system's lowest energy configuration, must be reconsidered. In equilibrium quantum physics, the ground state is static. It does not evolve in time, except for an unobservable global phase. But in periodically driven systems, a new kind of steady behavior becomes possible. These are known as Floquet states, named after the French mathematician Gaston Floquet. A Floquet system repeats its behavior with the same period as the drive, or in the case of a time crystal, with a longer period. These repeating states are not ground states in the traditional sense, but they can be stable and long-lived, occupying what physicists call a pre-thermal regime, where heating is effectively suppressed for a very long time. What makes this oscillation remarkable is that it does not perform work, nor does it require work to be performed. In a time crystal, motion becomes a form of symmetry breaking, not a thermodynamic process. The system is not converting energy from one form to another. Instead, it is moving because movement is the form of order it has selected. The oscillations are protected by the structure of the interactions, the presence of disorder, and the coherent evolution of the quantum state. The drive acts only as a reference, not as a fuel source. In classical terms, this would be impossible. If you repeatedly kick a ball with no friction, it will accelerate. If you drive a pendulum at its resonant frequency, it will swing more and more until it breaks or stabilizes at a high amplitude. But in a time crystal, periodic driving does not lead to cumulative motion or energy gain. It leads instead to a locked, repeating response, an echo, not an escalation. It is here that the quantum nature of time crystals asserts itself most powerfully. These systems rely on quantum coherence, entanglement, and interference. The particles that make up a time crystal, whether they are trapped ions, superconducting qubits, or other degrees of freedom, must remain entangled in a collective quantum state. The repeating behavior arises from the evolution of this entangled state under the influence of the periodic drive. The coherence of this evolution is what allows the system to remember its past and anticipate its future. It is not that energy is moving through the system, but that the system's internal configuration is cycling through a fixed set of states in a synchronized pattern. One way to visualize this is to imagine a line of dancers who, instead of moving across a floor, cycle through a series of poses at precisely timed intervals. They do not change location, they do not accelerate, but their configuration changes rhythmically, forever, without tiring or requiring fuel. The motion is entirely internal, defined by a pattern of changes that repeats in time. The energy remains constant, the entropy is managed by isolation and localization, and yet the system is not static. This is the essence of motion without energy. The robustness of time crystal motion also sets it apart. Most systems that oscillate or resonate are extremely sensitive to noise, dissipation, or disorder. But time crystals can withstand perturbations. The drive period can be slightly irregular, the interactions can be disordered, and the system will still oscillate with the same regularity. This is a hallmark of spontaneous symmetry breaking and phase formation. In a magnet, the orientation of the magnetic field persists even when the system is disturbed. In a time crystal, the temporal pattern persists for the same reason, because it reflects an internal structure that is not easily dislodged. This robustness opens the door to practical implications. Time crystals may serve as ultra-stable references for quantum clocks, or as resilient components in quantum computing architectures. Their ability to maintain coherence and periodicity in noisy environments could make them useful for error-resistant encoding of information. Though these applications are speculative, the principle is clear. Time crystals demonstrate that in the quantum world, order can arise not from stillness, but from carefully maintained rhythm. This insight challenges long-held assumptions. In both classical and quantum mechanics, equilibrium has often been seen as the final, most stable state of a system. Time crystals reveal a different kind of stability. one that exists far from equilibrium, protected not by energy minimization, but by dynamical constraints and quantum correlations. In doing so, they expand our understanding of what is possible in nature. They invite physicists to consider new classifications of matter, new taxonomies of phases, and new mechanisms of coherence and control. As experiments continue, researchers are exploring how far this principle can be extended. Can time crystals exist in higher dimensional systems or in topologically protected forms? Can they interact with their environments while maintaining coherence? Can we build devices that exploit their timing precision for real-world applications? These questions remain open, but the foundational insight that motion need not be powered will continue to reverberate. The phenomenon of motion without energy forces us to reconsider the relationship between time, energy, and change. In our daily lives, we are accustomed to systems winding down, to clocks stopping, to movement requiring work. But in the delicate architecture of quantum systems, motion can emerge not from push, but from pattern. It can exist not as a response to energy, but as a signature of order, woven into the very structure of the quantum state. And perhaps on a quieter level, this offers a philosophical resonance. In a universe that constantly trends toward disorder, where energy is spent and time is lost, the idea that something can move forever without consuming anything, without growing tired, without decaying, feels almost like a defiance of fate. A whisper from the quantum world that not all change demands a price, that rhythm once found can last. That motion can be a kind of stillness, repeating, perfect, and serene. Chapter 7. Are time crystals useful? The future of quantum phases. The discovery and experimental realization of time crystals mark a remarkable moment in modern physics, a theoretical speculation transformed into an engineered quantum phenomenon. But as the dust of novelty begins to settle, one question becomes increasingly relevant. Can time crystals be useful? Are they merely scientific curiosities, or could they become practical components of future quantum technologies? In an era defined by the rapid advancement of quantum computing and non-equilibrium physics, time crystals might indeed offer more than just philosophical wonder. They may signal the beginning of a new chapter in our ability to control and utilize exotic phases of matter that exist far from equilibrium. To begin assessing the utility of time crystals, one must first appreciate their most distinctive trait, their temporal rigidity. Unlike typical quantum systems that degrade over time due to environmental noise or thermal fluctuations, time crystals demonstrate a kind of phase-locked behavior. Their oscillations occur at precise intervals, dictated not by an external clock, but by internal dynamics that spontaneously break time translation symmetry. This intrinsic regularity offers a tantalizing opportunity. In a domain where timing, synchronization, and phase coherence are critical, such as quantum computing, structures that maintain rhythm without external control are of profound interest. One area where time crystals might find practical application is in the realm of quantum memory. In quantum computing, information is stored in the quantum states of physical systems, typically in qubits. Maintaining the integrity of these quantum states over time is a major challenge. Qubits are highly sensitive to environmental disturbances, and even tiny amounts of noise can lead to decoherence, in which quantum information becomes scrambled and unusable. A time crystal, by contrast, is inherently robust. It exhibits stable, periodic behavior that persists despite certain types of noise and imperfections in the system. This stability arises from a combination of many-body localization and the protective structure of its symmetry-broken phase. In such a regime, the time crystal becomes resistant to small perturbations, making it a candidate for storing information in a way that is less susceptible to external fluctuations. If researchers can harness the periodicity of a time crystal to define logical states in a quantum memory device, essentially encoding information in the timing of the oscillations, it might be possible to construct new forms of memory that are both persistent and energy efficient. Closely related is the possibility that time crystals could contribute to quantum error correction. This is a crucial area in quantum computing because quantum systems are inherently fragile. Small errors accumulate quickly in even the most sophisticated quantum circuits, and without effective error correction, large-scale quantum computation becomes infeasible. Time crystals, with their ability to resist decoherence and maintain structure over many cycles, could serve as part of an architecture designed to detect and correct deviations from expected behavior. For example, any deviation from the expected oscillation period in a time crystal could signal the presence of an error, triggering a correction protocol. This application remains theoretical, but research is underway to explore how the symmetries and constraints of time crystal phases could be incorporated into quantum error-correcting codes. Some of these ideas borrow from topological quantum computing, another field that leverages exotic quantum phases to protect information. While time crystals are not topological in the traditional sense, they share a related robustness. Their properties do not depend on microscopic details, but on macroscopic structure and symmetry. Another potential application lies in quantum synchronization. In classical engineering, synchronization is vital in systems ranging from electrical grids to communication protocols. The ability to synchronize components precisely over long timescales is a fundamental engineering challenge. In quantum systems, this task becomes even more delicate due to the sensitivity of quantum phases and the absence of classical reference frames. Time crystals, with their ability to maintain a fixed temporal order even when driven by imperfect or disordered pulses, could act as internal timing references, quantum metronomes that help synchronize other processes in a larger circuit. Such timing references might be useful in distributed quantum computing, where entangled qubits are spread across different physical locations. Establishing synchronized timing between remote systems is difficult, particularly when quantum coherence must be preserved. If a time crystal could be used to generate or lock timing between subsystems, it might play a role in stabilizing long-range entanglement or coordinating multi-part quantum operations. While this application remains speculative, it is grounded in the core behaviors that time crystals have already demonstrated in the lab. More broadly, time crystals belong to a new class of non-equilibrium quantum phases, a field that is still in its infancy. For most of the history of condensed matter physics, attention was focused on phases of matter in thermal equilibrium: solids, liquids, gases, superconductors, magnets, and so forth. These systems can be understood within the framework of equilibrium statistical mechanics, where energy minimization and entropy balance dominate the landscape. Time crystals, however, are fundamentally out of equilibrium. They require periodic driving and the careful interplay of disorder and interaction to stabilize their phase. This means they represent a different organizing principle, one that is not about minimizing energy, but about stabilizing patterns of motion. This opens the door to a much broader field of non-equilibrium phases and quantum materials. Just as the discovery of superconductivity revolutionized low-temperature physics, or the development of topological insulators redefined our understanding of electronic phases, the realization of time crystals may prompt a new taxonomy of matter, defined not by what is still, but by what repeats in time. Researchers are already beginning to explore generalizations of time crystals, such as time quasicrystals with more complex temporal patterns, or time crystals in higher spatial dimensions. Each extension challenges the boundary of what structured temporal behavior can look like in a quantum system. In this context, The utility of time crystals is not just a matter of immediate application, but of conceptual expansion. They allow physicists to explore new classes of phenomena, to test the limits of quantum coherence, and to design systems with entirely novel kinds of control. This is especially relevant as quantum simulation becomes an increasingly important tool. In quantum simulation, quantum systems are engineered to mimic the behavior of other, less accessible systems, such as high-energy field theories or exotic condensed matter phases. Time crystals could serve as both subjects and tools in such simulations. By using them to simulate the dynamics of symmetry breaking in time, researchers might explore phenomena that are otherwise inaccessible, such as early universe symmetry transitions or out-of-equilibrium field dynamics. There are also potential implications in metrology, the science of measurement. Time crystals could one day be used in designing ultra-stable frequency standards. Because they oscillate with precise subharmonic responses, they might offer an alternative method for defining time intervals, particularly in regimes where classical clocks are not ideal. These ideas remain highly theoretical, but they stem directly from the defining feature of time crystals: their intrinsic, persistent regularity in time. Despite the promise, it is important to maintain realism about the timeline and limitations. Time crystals, as currently realized, are small-scale systems involving only tens of qubits or ions. Scaling them up, integrating them into functional quantum devices, and maintaining coherence in more complex environments are formidable engineering challenges. Moreover, their sensitivity to specific conditions, such as the need for disorder and isolation, may limit their integration into more open and interconnected quantum systems. Still, these challenges are not unlike those faced by early quantum computing or superconducting systems, both of which have since progressed dramatically. The deeper utility of time crystals may ultimately be philosophical. They change the way we think about phases of matter and the role of time in physics. They illustrate that stable behavior does not require equilibrium, that repetition need not stem from energy consumption, and that coherence can emerge from dynamical structure rather than thermodynamic stillness. In this sense, they are reminders that nature's organizational principles are not exhausted by the familiar categories. New kinds of order remain to be discovered, orders in space, in time, and perhaps in domains we have not yet learned to name. Time crystals are not useful in the same way that traditional materials are useful. Not yet. They do not conduct electricity, bear loads, or store vast amounts of energy. But their usefulness lies in what they suggest is possible: that the laws of physics permit persistent, non-dissipative motion, that symmetry can be broken not just in space, but in time, and that phases of matter can form around cycles, not rest. These are not trivial insights. They are foundational. And perhaps in the gentle heartbeat of a time crystal, its quiet repetition, its rhythm without rest, we see something else. A reflection of the human desire to find structure in change, to build permanence not from stasis, but from motion. In a universe that moves toward disorder, here is a pattern that endures, not by resisting time, but by embracing it. Chapter 8. Time crystals in nature. Do they exist outside the lab? The realization of time crystals in laboratories using superconducting qubits and trapped ions marked a monumental shift in the study of quantum phases. These experiments confirmed that time crystals could exist under specific engineered conditions: periodic driving, quantum many-body localization, and isolation from external thermal environments. But this success raises a compelling question that reaches beyond the walls of experimental chambers. Could time crystals exist naturally? Are there systems in the universe where time translation symmetry breaks spontaneously without human intervention? In other words, are time crystals an artificial curiosity, or a hidden feature of nature waiting to be found? To approach this question rigorously, one must first clarify what is meant by a natural time crystal. In the laboratory, time crystals are created in systems that are designed to exhibit many-body quantum behavior under controlled, non-equilibrium conditions. This includes deliberately introduced disorder, precision-tuned couplings, and well-regulated periodic drives. These are not typically conditions one finds easily replicated in natural environments. Therefore, the search for natural time crystals is not simply a matter of spotting a repeating signal in nature. It is about determining whether the physical universe naturally supports the long-term coherence, isolation, and temporal ordering required for time crystal phases to emerge spontaneously. The first avenue for exploration involves high-energy astrophysical environments. In regions such as the crusts of neutron stars, matter exists in highly exotic phases. Neutron star interiors host some of the densest known matter in the universe, where quantum degeneracy pressure and intense gravitational fields create unique conditions. The crust, composed of tightly packed nuclei and degenerate electrons, may behave like a quantum solid in some regimes. It is here that researchers have speculated about the possibility of time crystalline behavior emerging due to strong interactions, spatial periodicity, and potential disorder from nuclear reactions or crustal deformations. The periodic structures in neutron star crusts, sometimes called nuclear pasta, exhibit repeating spatial patterns, but whether these could be accompanied by spontaneous temporal ordering remains an open and highly speculative question. One of the primary barriers to such natural time crystals is the issue of energy input. Laboratory time crystals rely on periodic driving, regular pulses or cycles introduced from the outside. Without this, the dynamics of the system do not break time translation symmetry in the same way. However, in astrophysical environments, natural drivers do exist. Rotational precession, tidal forces from companion stars, and magnetic oscillations might serve as natural analogs to periodic drives. In principle, a system subjected to such environmental cycles could experience a form of temporal resonance, where internal dynamics synchronize to a subharmonic of the external periodicity. If that subharmonic response were stable and long-lived, it could resemble time crystal behavior. Whether such oscillations would qualify under the strict definition of a time crystal, requiring robustness, spontaneous symmetry breaking, and non-equilibrium stability, is another matter. More promising might be the early universe. During the inflationary epoch, the universe underwent rapid, exponential expansion, driven by a quantum scalar field. During this period, quantum fluctuations were stretched to cosmological scales, seeding the structure of galaxies and cosmic microwave background anisotropies. Some speculative theories propose that time crystalline phases could have formed in this exotic, high-energy setting. Here, time periodic fields could, in principle, break symmetry in a way analogous to time crystals. Scalar fields with oscillatory potentials might have settled into repeating behaviors across time, leading to structures not just in space, but in the temporal evolution of fields. These proposals remain theoretical, lacking direct observational signatures, but they demonstrate that cosmology may offer fertile ground for exploring time symmetry breaking phenomena at universal scales. Another angle is provided by condensed matter systems in nature that may accidentally replicate some of the conditions found in laboratories. Certain driven systems, such as charge density waves in solids, oscillating magnetic phases, or even biological rhythms, exhibit periodic behavior. However, most of these are not time crystals in the strict sense. Their periodicity is often externally enforced or thermodynamically unstable over long periods. Biological clocks, for instance, operate through dissipative cycles involving energy metabolism and feedback loops. These systems do not display the same kind of spontaneously broken, subharmonic temporal symmetry protected by quantum coherence and disorder. Nonetheless, the line between engineered and natural can blur. If a system were discovered in nature that showed a subharmonic response to a naturally occurring drive with stability, coherence, and resistance to decoherence, it could raise the possibility that time crystals do not require the laboratory. They simply require the right conditions. It is also worth noting that the universe itself operates under strict symmetries, many of which are spontaneously broken. From spatial translation to rotational invariance, symmetry breaking underlies the development of structure in the cosmos. That time might also be subject to spontaneous symmetry breaking is not a foreign idea. In fact, some theories suggest that the arrow of time itself may be an emergent property, arising from the initial conditions of the universe or the behavior of entropy in complex systems. While these ideas do not directly imply time crystal formation, they suggest that time, like space, may support ordered, broken symmetry states under the right circumstances. There is a subtlety, however. Time crystals, as they are currently defined, require periodicity. They must exhibit repeating patterns in time that are not trivially imposed but emerge from the dynamics of the system itself. This raises a conceptual challenge when considering the possibility of time crystals in continuous, large-scale systems. Most natural systems are not closed. They interact with environments, experience noise, dissipate energy, and exchange heat. Time crystals are exceptionally sensitive to decoherence. Maintaining the entanglement and coherence necessary to stabilize their phase requires near-perfect isolation, something exceedingly rare in natural settings. For this reason, most researchers believe that if time crystals do occur in nature, they would do so only in small, shielded systems, perhaps in isolated pockets of low-temperature matter, or in microenvironments where disorder, periodic driving, and coherence coexist. Alternatively, one might find precursor phenomena, systems that exhibit some characteristics of time crystals without fully satisfying the theoretical criteria. These might include long-lived oscillations in condensed matter systems, unusual frequency locking in driven disordered systems, or exotic field configurations in cosmological models. One experimental direction seeks to move the laboratory itself closer to nature. Rather than requiring perfect isolation, scientists are beginning to test time crystals in open systems, those coupled to environments, exposed to noise, and subject to dissipation. The goal is to discover whether time crystalline behavior can survive in less ideal conditions. Success here could suggest that time crystals are not as fragile as once thought, and might in fact arise in less controlled, even natural environments. This line of inquiry aligns with the broader trend in physics towards studying non-equilibrium systems that operate in real-world conditions. The classical framework of equilibrium thermodynamics is giving way to a richer understanding of systems that live in a perpetual state of imbalance, driven by energy, noise, or other dynamic influences. In this wider paradigm, time crystals may not be exceptions, but exemplars of how order can arise far from thermal rest. Even in quantum biology, a field still emerging and highly debated, the potential for coherent quantum processes in biological systems has led to speculation about time-symmetric structures in molecular systems. Though no time crystal has been found in biology, and such a discovery remains far-fetched at this stage, the broader implication is clear. Life itself thrives on rhythms, circadian cycles, cardiac pulses, oscillating gene networks. These cycles are not time crystals, but they show that time-structured behavior is a universal feature of complex systems. Whether the quantum mechanical analog of this order can emerge spontaneously in natural systems is still an unanswered question. As the search continues, theorists are developing models of generalized time crystals, systems that may not strictly follow the canonical definition, but which capture its essential features: long-lived temporal order, robustness, and symmetry breaking. These models may help us better understand how to look for signs of time crystals in places we haven't yet considered, or perhaps even reinterpret familiar systems through a new lens. Ultimately, the question of whether time crystals exist outside the lab is not just about confirming a prediction. It's about understanding the limits of spontaneous order. It's about discovering whether the fabric of time itself can support patterns not imposed, but chosen, emergent structures in the stream of moments. Whether in the dense heart of a neutron star, the cold vacuum of the early universe, or the carefully tuned chamber of a quantum processor, the possibility remains that time itself may harbor symmetries waiting to break. And perhaps, somewhere out there, a system cycles in perfect rhythm, untouched by observers, free of purpose or decay, a quiet pulse repeating forever. Not seen, not recorded, not built, just there. A clock without a maker, a movement without a cause, a whisper, lost in the vastness of time. That structure can emerge even in its flow. Chapter 9. Time, Repetition, and the Illusion of Change. Time is a deeply embedded concept in both physics and human experience. It structures our understanding of motion, change, cause, and effect. It appears to flow, to push events from the past into the future, creating a sequence that we interpret as history, experience, and memory. Yet when we examine time at the quantum level, especially through the lens of phenomena like time crystals, this intuitive sense of linear progression begins to unravel. In systems that move forever in a cycle, without consuming energy or progressing toward equilibrium, we are forced to question, what does it really mean for something to change? A time crystal, as we have explored, is a system that repeats itself in time. Its internal configuration evolves from one state to another in a regular pattern, such that after a set interval, the system returns to its initial condition. This is not merely periodic behavior like that of a pendulum or a heartbeat. Unlike classical systems that require a continuous input of energy to sustain motion, time crystals exhibit a fundamentally quantum form of persistence. Repetition without decay, oscillation without energy cost. The system changes in a precise, measurable way, yet it is locked into a rhythm that never deviates. From one cycle to the next, everything is the same. It is a form of change that contains no progress. This kind of behavior challenges the conventional relationship between time and entropy. In thermodynamics, the arrow of time is closely linked to the second law, which states that entropy, the measure of disorder in a system, tends to increase. This increase defines a direction for time. A broken glass does not spontaneously reassemble. Heat flows from hot to cold. Systems left to themselves evolve toward equilibrium, and this is what gives our experience of time its asymmetry. But time crystals, by contrast, are structured to resist entropy. They avoid thermalization through many-body localization or pre-thermalization, allowing them to maintain order indefinitely, or at least for extremely long timescales. In a time crystal, entropy does not increase in the traditional sense, even though the system is being driven periodically. The periodic drive, often viewed as a source of disorder, does not heat the system or lead to decoherence, provided certain conditions are met. Instead, the drive becomes part of the system's structure, like the beat of a drum to which the internal components respond with a stable rhythm. This dynamic raises fundamental questions. Is the system really changing, or is it merely retracing its steps in a closed loop? Can motion exist without a net transformation? From a quantum mechanical standpoint, evolution is deterministic and unitary. The wave function of a closed system evolves smoothly and reversibly according to the Schrödinger equation. If no measurement is made and the system remains isolated, its state will continue to evolve in a manner that is, in principle, predictable and reversible. In this light, time itself appears more like a parameter, a label for the evolution of the wave function, rather than an active agent of change. This interpretation is starkly different from our intuitive sense of a flowing time. It suggests that what we perceive as change might be better understood as a pattern of relations, an unfolding of quantum correlations that do not require the passage of time as we experience it. Time crystals amplify this tension. They evolve in a cycle, but their motion is confined. The state at time zero returns after a fixed interval. Observers outside the system can see the oscillation, measure the changes, and confirm that the system is not static. Yet within the system's own structure, nothing is advancing. There is no accumulation of entropy, no permanent memory of past configurations. Everything repeats, again and again. To the observer, there is change. To the system, there is only repetition. This leads to a fascinating analogy with broader philosophical questions about the nature of time and experience. In many mystical and philosophical traditions, the concept of cyclic time has existed for millennia. Ancient cultures conceived of time not as a straight line, but as a circle, one in which events repeat in endless loops. Seasons cycle, celestial bodies orbit, and myths recur with minor variations. In modern physics, the cyclical behavior of time crystals echoes this ancient vision, not symbolically, but literally. They are systems where the past returns, again and again, not as metaphor, but as state evolution. From this perspective, the illusion of change becomes an emergent property of periodic systems. Repetition can generate the appearance of transformation, even if the underlying dynamics are constrained to a closed loop. In everyday life, the ticking of a clock measures time, but it is also a perfect example of constrained repetition. Each tick is identical to the last in form, but we interpret it as a sign of forward movement. Time crystals present a similar paradox. They provide a measurable unit of temporal change, an oscillation, a phase shift, a quantum transition. Yet the overall structure does not evolve toward anything new. This raises the question of whether novelty is a necessary feature of time. If a system changes but never moves away from its starting point, is it truly experiencing time, or is it simply encoding a symmetry in motion? And if systems can exhibit stable, repeating behavior without loss or gain of information, what does this say about the arrow of time itself? Some theoretical models have explored whether time's arrow could be an emergent property, not fundamental, but the result of statistical behavior in complex systems. In such models, the directionality of time arises from the conditions of the observer and the environment, not from any intrinsic property of the laws of physics. Time crystals, which live in a space where order is preserved indefinitely, may hint at what systems look like when the arrow of time is neutralized or reversed. They offer a controlled setting in which time does not push systems forward into disorder, but instead loops them back to familiar configurations, again and again. These insights also invite deeper reflection on the nature of change in the quantum world. In classical mechanics, a system changes by moving through configuration space, a set of positions and velocities that describe its state. In quantum mechanics, a system evolves through Hilbert space, a much larger and more abstract space of probabilities, amplitudes, and superpositions. A time crystal state evolves within this space in a closed, unitary trajectory. It returns to itself not by retracing a classical path, but by reconstructing its quantum correlations through interference and coherence. This evolution is invisible to classical intuition, but mathematically precise. Interestingly, this kind of periodicity in quantum systems is not limited to engineered time crystals. Certain phenomena, such as Rabi oscillations, also exhibit coherent periodic behavior in two-level systems under resonant driving. However, these oscillations are not robust phases of matter. They decay over time and depend on fine-tuned conditions. What sets time crystals apart is their resilience and the role of symmetry breaking. In a time crystal, the oscillation is not externally imposed. It is an emergent property of the many-body system, stabilized by interactions and protected by symmetry. This emergent regularity suggests that change may not be about moving forward, but about maintaining structure within transformation. In other words, change is not the enemy of order, but its expression. A time crystal changes constantly, yet it never degrades. It repeats, not because it is trapped, but because repetition is the form its coherence takes. And if repetition can be a kind of stability, perhaps our understanding of time needs to evolve. Time need not always be an arrow pointing toward oblivion. It can also be a circle, a rhythm, a pattern. In the quantum world, where particles entangle, decohere, and evolve in ways far removed from classical intuition, time may be less of a flow and more of a scaffold, a structure that supports recurrence, coherence, and symmetry. This reframing has implications far beyond physics. In human experience, time is deeply psychological. It is memory and anticipation, regret and hope. We mark it with calendars, clocks, and stories. We strive to escape repetition, to make progress, to evolve. But if time crystals show us anything, it is that repetition is not stagnation. It is a kind of motion, a structured dance, a quiet resilience. In the quantum world, where cause and effect blur, change and repetition may be closer than we think. Perhaps then, the deepest illusion is not that time flows, but that it must lead somewhere. In the heart of a time crystal, change is constant, but nothing is lost. The system turns back on itself, again and again, perfect in its rhythm. And in that perfect circle, we might glimpse a new understanding, that time is not a river, but a song. Chapter 10. The Stillness That Moves. Why Time Crystals Matter. In the vast taxonomy of matter, time crystals occupy a peculiar and fascinating niche. They are not defined by structure in space, but by structure in time. Their periodicity is not a function of motion through a classical landscape, but a rhythm that emerges from the internal quantum dynamics of a system. At first glance, the realization of time crystals may seem like a narrowly defined breakthrough, a clever twist in the long history of symmetry breaking in physics. But their importance reaches beyond novelty. Time crystals matter because they challenge our assumptions about time, energy, order, and the nature of physical laws themselves. They hint at a deeper stratum of structure in the universe, one where change can be stable, motion can occur without energy, and time itself can acquire crystalline regularity. The scientific significance of time crystals is multidimensional. On a fundamental level, they reveal new possibilities for how matter can organize itself under conditions far from equilibrium. For more than a century, much of condensed matter physics has focused on phases of matter in equilibrium, states where thermodynamic quantities like temperature, pressure, and entropy settle into a stable balance. Solids, liquids, gases, superconductors, ferromagnets, all of these are equilibrium phases. Their properties are governed by energy minimization and entropy maximization. Time crystals defy this framework. They are inherently non-equilibrium phases, requiring a periodic drive to exist, yet managing to avoid the runaway heating or chaotic behavior typical of driven systems. This makes them one of the first experimentally confirmed examples of a new class of phases that are stabilized by dynamic conditions rather than static ones. Such phases open the door to a much broader understanding of what matter can be. They suggest that the classification of physical systems cannot end with equilibrium states. Just as the discovery of topological phases reshaped how physicists think about electronic materials, introducing concepts like topological insulators and quantum Hall states, time crystals point toward a growing recognition that matter can have dynamic order, not just static structure. The defining feature of a time crystal is not its composition, but its behavior, a stable, repeating oscillation in time that emerges spontaneously and resists disorder. This behavioral definition is a shift in how physicists think about phases, one that emphasizes evolution over configuration, rhythm over geometry. Equally important is the role time crystals play in deepening our understanding of symmetry. Physics, at its core, is about symmetries and the consequences of breaking them. Noether's theorem tells us that symmetries correspond to conservation laws. Spatial symmetry corresponds to conservation of momentum, time symmetry to conservation of energy, and so forth. The spontaneous breaking of spatial symmetry gives rise to crystals. The spontaneous breaking of gauge symmetries leads to phenomena like superconductivity. Time crystals represent a new kind of symmetry breaking, one that applies not to space or internal degrees of freedom, but to the very flow of time itself. This is more than an academic distinction. It demonstrates that time translation symmetry, once thought to be inviolate in closed systems, can be broken in controlled, reproducible ways. Time crystals do not violate energy conservation, nor do they enable perpetual motion machines in the classical sense. Rather, they show that symmetry breaking in time is possible under periodic driving and many-body localization. This realization enriches the conceptual toolkit of physics, offering a new axis along which systems can be classified and understood. From a technological standpoint, time crystals may eventually serve as robust elements in quantum devices. Their stability under periodic driving, resistance to decoherence, and intrinsic timing precision make them candidates for use in quantum memory, synchronization, or even error-resistant computation. While these applications remain speculative, the foundational work being done today could influence how we design future quantum architectures, particularly those that need to operate reliably in noisy or non-equilibrium environments. Whether or not time crystals become integral components of quantum technology, the insights gained from their study will continue to inform how quantum systems are built and controlled. But perhaps the deepest reason time crystals matter lies in what they reveal about time itself. In classical physics, time is an external parameter, a neutral backdrop against which events unfold. In general relativity, time is part of space-time, warped by mass and energy. In quantum mechanics, time plays a peculiar role. It drives the evolution of wave functions, yet is not itself unobservable. This asymmetry between time and other physical quantities has long troubled physicists seeking a unified framework for quantum gravity or a theory of everything. Time crystals, by introducing order into time through quantum behavior, suggest that time may not be as passive as previously believed. If matter can organize itself temporally as well as spatially, then time may have an internal structure, or at least the capacity to support structured dynamics beyond mere parameterization. This idea remains speculative, but it offers a provocative hint that time might participate in the symmetry-breaking processes that give rise to complexity, just as space and internal symmetries do. Moreover, time crystals force us to reconsider the relationship between motion and energy. In classical systems, motion is inextricably linked to energy. A mass in motion has kinetic energy. A pendulum swings until friction robs it of energy. A planet orbits as a balance of kinetic and gravitational potential. But in a time crystal, motion occurs without traditional energy expenditure. The system is driven, yes, but it does not absorb that energy in the usual way. It does not heat up or randomize. Its motion is a signature of quantum coherence and many-body interactions, not mechanical work. In this sense, time crystals decouple motion from energy in a way that classical physics does not allow. This decoupling is not only conceptually surprising, it is also practically significant. It points to new ways of sustaining coherent behavior in driven systems, which is one of the central challenges in building scalable quantum devices. The creation of time crystals also underscores the growing power of quantum simulation as a scientific method. The laboratory time crystals built so far, using trapped ions or superconducting qubits, are not large, naturally occurring objects. They are engineered systems, constructed and manipulated with unprecedented precision. Their success is a testament to how far experimental physics has come in mastering the delicate manipulation of quantum systems. It also reflects a larger trend, the increasing use of programmable quantum systems to explore fundamental questions. In a sense, time crystals are a proof of concept, not only of a new phase of matter, but of a new paradigm in scientific discovery, one where experiments are not just tests of theory, but platforms for exploring entire classes of phenomena. In the end, the true importance of time crystals may not be in any one application or theoretical breakthrough. It may be in what they represent, the capacity of the physical world to surprise us, even in areas we thought were well understood. The idea that time itself could host ordered phases, that motion could persist without energy, that symmetry could be broken in temporal dimensions, these are not small insights. They are reminders that the universe is deeper, stranger, and more layered than our current models can fully explain. Time crystals are unlikely to power spacecraft or solve global energy problems. They will not rewrite thermodynamics or overturn relativity, but they will continue to refine our understanding of what time, motion, and matter can mean. They will inspire new questions, guide new experiments, and perhaps lead us toward a more complete theory of quantum dynamics. In doing so, they fulfill the highest aspiration of physics, to reveal new possibilities within the laws of nature, and to remind us that even the most familiar concepts, like time, may hold secrets still. And perhaps in their silent oscillations, in their stillness that moves, we see a reflection of something enduring. Not all change must be progress. Not all motion must be linear. In the recursive, quiet symmetry of the time crystal, there is a whisper that some things do not move forward, but deepen. And that, my friend, was the quiet heartbeat of a time crystal, a motion that never tires, a rhythm hidden in the fabric of reality. If you're still awake and want to keep drifting through the universe, there's another video waiting just for you. But if your eyes are already heavy, then sleep well, and may your dreams unfold slowly among the stars.